My name is Alex, and my project for formal languages and computability is the traffic intersection validator. To preface why I chose to do something as innocuous as a traffic validator, it is because you really don't think much about it or its functions. It's just something we interact with in our daily lives when either driving or walking across a road. It is just an automated system that we obey to stay safe. With over 300,000 existing intersections in the United States alone, and approximately 2,550 new additions each year, we need to ensure that these systems work and adhere to the correct traffic sequence. A malfunction on any aspect of the traffic system could mean the difference between life or death, so my motivation was to create a DFA that validates these sequences and provides feedback to those necessary to keep the systems working properly. The DFA, pictured to the right, is a trigger-based model that takes into account the traditional stoplight, the crosswalk, and the turn-only arrow stoplight. A trigger-based model is when a car or person enacts one of the subsystems. Per se, if a car pulls up to a red stoplight, the stoplight sequence of green, yellow, and red is added to the string to be executed. When creating my DFA model, I started with a minimal viable product approach, working from the basis of the simple green, yellow, and red light and adding more complexities as I completed portions. I took this approach so I can build each subsystem and then integrate it into an existing model, ensuring that the systems can be decomposable. Each subsystem has their own accepting states, so that can work independently in addition to cohesively. All in all, the DFA was accomplished using 9 states, with a start state of Q0 and final states of Q0, Q5, and Q7. Some things to note on the DFA are that each state has the previous transition function looped into itself. This acts as a makeshift time function, so depending on how many triggered a subsystem gets, it will execute that a number of times. Furthermore, the DFA was built with one of the traffic flow hierarchies in mind, meaning that if both the crosswalk and the turn-only arrows are triggered in the same sequence, the crosswalk function must be executed before the turn-only. Otherwise, the series is considered. Now looking at the user interaction with the DFA, it's a relatively simple input and output model with a key at the top. The reason for the simple display is because, ideally, if the DFA was to be implemented in the real world, the DFA would interact with the traffic system itself in real time, flagging any and taking necessary actions if the traffic sequence is wrong. For the purpose of this project, it is a human inputted string. Each action is assigned with a key value pair made to input the traffic sequences easier. Looking at some example of correct traffic sequences, it is very straightforward when you input a correct string. As I mentioned earlier in the presentation, the system is decomposable into subsystems with their own respective accepting states. If you look at the crosswalk, traditional traffic light, and turn-only light sequences, they are correct when inputted on their own. This is beneficial if you want to isolate certain segments of an intersection and have individual ports on the system. The DFA can also evaluate the subsystems sequenced in with one another and support multiple loops in the same string iteration. This is important because it enables the DFA to be scalable. So if somebody wants to evaluate an intersection that does not have a turn-only signal, but has a traffic light and a crosswalk, the DFA can still evaluate the sequence without any interruptions. One of the improvements that I made on my DFA model was a meaningful feedback if the string was invalid. Nothing is more annoying, especially on a more extended string sequence, to be told that it is just wrong and nothing further. So I made sure not only to say to the user that the string was invalid, but also at what index the string is invalid, the input value in clear text, as well as the values the DFA was expecting. There are 3 feedback models that I have created for incorrect sequences. Shown on this slide is an incorrect series, in which a character in the string is entirely wrong. The string starts off with green, yellow, and red lights, and then jumps to a yellow turn arrow. The DFA states that, instead of the yellow turn arrow, it was expecting either a green light, green turn arrow, or safe to cross the crosswalk at the 3rd index, which is why the string is invalid. Another model in the inputted string contains an illegal character. This model is useful, especially in extending strings, because the index points out where the character is in the string so the user can correct the error. The last invalid model that I included was a correct but unfinished sequence, meaning that the string was valid up until the last character, but did not end on an accepting state. I added this test case because I want to let the user know the string is wrong, but on the right sequence path. The example on the slide shows a sequence that starts off with the green and yellow light and ends there. This sequence is almost complete, so the DFA lets the user know the string is invalid because it did not end in an accepting state, and lets the user know that the red light is needed to progress to the next state, which would ultimately yield a valid sequence. With this, it is the end of my presentation. If you have any comments or feedback, I look forward to hearing them. Other than that, thank you for listening.